Hello viewers, welcome to Famous Julius Academy. In today's video, we shall be looking at the derivation of three equations of motion using differentiation as a method. Now, we have other method to get the equations of motion, but today we shall be more precise using differentiation and integration. In this part of the board, I'm going to write the three equations of motion, then we are going to derive them using differentiation and integration. The first equation of motion is V is equal to U plus 8. Second equation of motion is x is equal to ut plus half 8 squared. And the third one is v squared is equal to u squared plus 2as. X here is displacement, but in differentiation we can use this x to represent displacement. So, as I said earlier, we are going to be using differentiation and integration to get these three equations of motion. If you look at the first equation of motion there, you notice that we are having a relationship between velocity, acceleration, and time. And this can actually be gotten from the formula of acceleration, because acceleration is actually the rate of change of velocity, which is v minus u over t. If you cross multiply from here, you notice that v minus u times 1 will give you v minus u equal to 8 times 6 which is 8. If you take minus u to that side, you're going to have v equal to u plus 8, which is actually the first equation of motion. So that means the first equation of motion was gotten from the formula of acceleration. But here we are going to be using acceleration in derivative form. Acceleration has two formulas. Acceleration can either be second derivative of displacement, which is d square x over dt square, or it can also be the first derivative of velocity, which is the v over dt. These are the two formulas for acceleration. Then we have for velocity. Velocity is the first derivative of displacement, which is dx over dt. So look at acceleration and velocity. Acceleration is second derivative of displacement, which is x, while velocity is first derivative of displacement. So if I differentiate this one again, I'm going to have acceleration. So the second derivative of this guy is square x over dt square. Now let's see how we can put all of this together to get these three equations of motion. Before I proceed, I want you to have some basic idea on integration, because we are going to be using integration while resolving all this. So if I have integral of x to the power of n with respect to x, is simply going to be equal to x to the power of n plus 1. I'm adding 1 to the power, multiplied by n over n, which is n plus 1. But let me assume I have something like this now. Integral of x to the power of 3 dx. What will I do? I will add 1 to 3. That's going to give me 4. We're going to have x to the power of 4 all divided by 4. That's all. But we can attach a constant of integration. The reason why we are attaching a constant of integration is because this integral is an indefinite integral. But respect to what we are going to be dealing with today, we are not dealing with indefinite integral, we are dealing with a definite integral. So when we resolve a definite integral, we don't usually attach a constant to it. Let me assume that I have the first case. Let me say integral of x squared dx. How will I resolve this now? I'm going to have this guy to be x to the power of 3 over 3. I added 1 to the power. But if I attach a constant here, let's say this is 0 and this is 1, this type of integral is called a definite integral. In this case, I will not attach a constant. Rather, what will I do? I will plug in the upper value of x, which is 1 for x. I will also plug in the lower value, which is 0 for x. I will subtract both of them. So if I do that, I'll first of all add, anywhere I see x, I'll put 1 there. So x squared become 1 raised to power 3 over 3. What have I done? I've turned x to 1. Then minus, I also turn x to 0. I'm going to have 0 cubed over 3. Like that. I will get my answer. So we are going to be using this tip to solve questions here. So now let's go with the first one. Remember, I said first equation of motion was gotten from the formula of what? Acceleration. So which of the acceleration formula are we going to use? Is it this one? Is it this one? We are going to be using the second one here. We are going to be using the second one. Here we have velocity, we have time, we have acceleration. We have velocity, we have time, we have acceleration. So in that case now we can see acceleration, which is the first derivative of velocity, the v over dt. We are going to cross multiply from here. We are going to have dv equal to a dt. So there's something I would like you to take note of. If I'm integrating a constant, let's say the constant is a number that does not have an alphabet attached to it. This is a constant. If I'm integrating this constant with respect to a particular variable, let's say the variable is x, I will just attach x to the number, which is 2. I'm going to have 2x. That's how to integrate that. But if I'm integrating the x alone, I will notice that there is usually an invisible number here. The invisible number is what? 1. So this will now be 1x. This entity has x. So the integral of dx is x. So now let's continue. Let's integrate both sides. We are going to integrate both sides. We take the integral of this side, we take the integral of this side. So we are going to say integral of the v, since integral of the x is x, integral of the v is going to give us v. Y integral of a dt is going to give us, let's assume a is a constant and this one is the variable we are differentiating in respect to. So we are integrating in respect to. So we are going to have 80. Here we have 2x is going to be 80. So we have 80. But remember, in this case, we are not using a indefinite integral, but we are using definite integral. So since we are using definite integral, we have a boundary. So this is going to be initial to final, while this one is going to be initial time t0 to t, time at 0 and time at t. So if you apply that same constant, we have from u to v, we also have from t0 to t. Using this method, we are going to first of all going to substitute v for v. We are going to have v minus u is equal to, we are going to change t. First, change t for t, we see same as t, at minus at0. Now t0 means time at 0 seconds. Time at 0 seconds is 0. So we are going to have v minus u is equal to at minus 0. And if you subtract it from 0, same thing. So we are going to have v minus u is equal to at. So if I take minus u to that side, we are going to have v is equal to u plus at. This is the first equation of motion. So we go to the first equation of motion. Let's now derive the second equation of motion. So let's see what we are going to do. We have the first equation of motion, v equals to u plus at. Let's see the second equation of motion. The second equation of motion, we are going to use the, notice we have displacement here, we have acceleration, and we have time. So we can use the velocity formula. Velocity is first derivative of displacement. So we say v is equal to dx over dt. First derivative of displacement. So we can cross multiply from here. We are going to have dx is equal to dt. The next thing we are going to do here is that we are going to replace our value of v with what we got initially. What is v? U plus 8. So I'm going to replace this v with u plus 80. So my equation becomes dx is equal to u plus 80 then dt. Now we can now integrate both sides. And we integrate this side, also integrate this side. So if I integrate dx, we are going to have x. Integral of dx is going to give us x, which is equal to, integrate u with respect to t. We talked about that before. We are going to say ut plus integrate at with respect to t. So it's just like if you want to integrate 2x with respect to x. What are we going to do? Remember that this guy has a power of 1. So we are going to have 2x whose power of 1 plus 1 is 2 all over 2. We can do the same thing here. We are going to have at squared over 2. So now if you look at this and look at this equation, we are the same. X, but we have to change this displacement x. This one is x. X is equal to ut plus half at squared. Ut plus half at squared. This is the second equation of motion. So let's see the third equation of motion. I'm going to go back to the third equation of motion. The third equation of motion, we are going to use a trick to deal with that, because here we have velocity, we have acceleration, and we have displacement. The three of them are there. We have velocity, we have acceleration, we have displacement. So we are going to combine two things here. We already know that acceleration A is equal to dv over dt. So we are going to look for a trick because what we have here, we only have acceleration, we have velocity, we have time. Acceleration, velocity, but there is no time. That means this time is not relevant. So what we are going to do is we can use a trick because dv over dt can also be equal to, if I times this by dv, let's say you can say dv over dx. Will this work out? This will not work out because if I multiply this, we are going to have this v times dv squared. So it's not going to work out. So we look for a trick to use so that we can have an expression that will cancel out the dt. So we are going to look for a trick to do that. And that trick will be, so we can say acceleration was v over dt. I can say acceleration will now become v dv over dx. Let's see if this is true. V dv over dx. Let's see, what is velocity? Dx over dt times, what do we have here? Dv over dx. What will happen? If this cancels this, we are left with dv over dt. Dv over dt. So that is correct. That means these two things together is the same thing as dv over dt. That is the trick that we are going to use here. So from here, since we know this is going to work out, this is the same thing as saying a equal to v dv over dx. If we now cross multiply from here, we are going to have v dv is equal to a times dx with a dx. So let's bring this back to the board and finish the derivation. So we have v dv is equal to a dx. What do we do from here? I've actually used a method which we call variable separator. If you look at this v and dv, they are like things. So I've separated them. So I'm going to integrate both sides. Integrate this side, integrate this side. So I'm integrating v with respect to the v. As we know, we're going to have here v squared over 2. But we are still dealing with a definite integral. That means we have boundaries. We are moving from initial to final. Here in displacement, we are moving from initial displacement to the final displacement x. So we are having u to v is equal to, if we integrate a with respect to x, we are going to have ax, we've seen that before, from x naught to x. So if we put our values for our upper and lower limits, what are we going to have? We're going to have v squared over 2 minus u squared over 2 is equal to ax minus ax naught. So what is x naught? X naught is the initial displacement. That means before your body starts moving, the displacement is 0. So x naught is 0. So we are going to have a times 0 is 0. So we now have v squared minus 2 minus u squared over 2 is equal to ax. This is already 0, so there's no need for us to attach that to it. So from here, we need to remove these denominators, which is 2. We look for the LCM. The LCM is 2. We are going to multiply all the terms here by 2. And multiply this side by 2, here by 2. So I'm going to say 2 times v squared over 2 minus u squared over 2 times 2 equal to ax times 2. What have I done? I've multiplied each of them by 2. The three of them. So that 2 can cancel 2. 2 can cancel 2. So here I'm going to be left with v squared minus u squared is equal to 2 times ax is 2ax. So if I take u minus u squared to that side, I'm going to have v squared is equal to u squared plus 2ax. And if you check this and check the third equation of motion, we have v squared u squared plus 2ax. Just the displacement to change the letter to this. So that is it. This is how we can get the three equations of motion using differentiation and integration. So for more exciting videos like this, please don't forget to like, to share, and to